So imagine that we have a box containing a parallelogram, a rectangle, a rhombus, and a square. Let's figure out the probability of picking out each of the following. So in total, there are four shapes in this box. So I know that this probability is going to have to be out of four. And we want the probability that a quadrilateral has congruent diagonals. So we know that congruent diagonals is a property of a rectangle. And if it's a property of a rectangle, it also applies to a square because a square is both a rectangle and a rhombus. So that's all the properties of both. So that's 2 out of 4, which simplifies to 1/2, or a 50% chance of pulling that shape out. A quadrilateral with diagonals that bisect each other. So once again, there are four shapes in this box, and diagonals that bisect each other is a property of parallelograms. And since rectangles are parallelograms, they also have this property. Since rhombuses are parallelograms, they also have this property. And since squares have properties of both rectangles, rhombuses, and parallelograms, squares have this property as well. So that's 4 out of 4, which simplifies to 1. So that's a 100% chance of pulling out a shape from this box that has diagonals that bisect each other. And finally, a quadrilateral that has only one pair of parallel sides. So there are four shapes in total, once again, and all of these shapes have to start off as parallelograms. And we know that parallelograms have two pairs of parallel sides. Both pairs of opposite sides need to be parallel. So none of these shapes has only one pair of parallel sides. So that's a 0% chance of pulling that out of the box. So our focus today is going to be on trapezoids in this video, which are quadrilaterals that have only one pair of parallel sides. So if you take a look at the quadrilateral family tree, you'll see that we have all our parallelogram-based quadrilaterals, rectangles, rhombuses, and squares that all need to start off as parallelograms, and trapezoids, which are separate. Trapezoids don't necessarily have to be parallelograms. The definition I'm using here is a trapezoid if it has only one pair of parallel sides, but you might see in some places that a trapezoid is defined as a quadrilateral with at least one pair of parallel sides. So the answer to the question here is technically yes. It depends on which definition you go by. But if your quadrilateral has only one pair of parallel sides, then it's for sure not a parallelogram. Then it's for sure a trapezoid. Because to be a parallelogram, it does need to have two pairs of parallel sides. Both pairs of opposite sides need to be parallel to be a parallelogram. So here we have a quadrilateral and we don't know anything about it. And the first question is asking us to find the measure of angle B. So I know that in the quadrilateral, all four angles need to add to 360 degrees. And two of the angles here are 90 degrees and one is 30 degrees. So I'm going to use my calculator and I am going to add up 90 plus 90 plus 30 and I get 210. I'm going to subtract that from 360 and I get 150 degrees for the measurement of angle B. The next question says to explain why ABCD is a trapezoid. So, by definition, a trapezoid has only one pair of parallel sides. And I see here that angle A and angle D, if I highlight the lines forming them and the transversal in between, I see that angles A and angle D are both inside the lines and both to the right of the transversal. So they are same side interior angles. And guess what? They're supplementary. 90 plus 90 makes 180 degrees. And we know that one of our ways of proving that lines are parallel is to show that same side interior angles are supplementary. So since our same side interior angles are supplementary, the lines forming them, AB and DC, are parallel to each other. And if we take a look at AD and BC, we'll see that we have 90 and 30. 90 plus 30 doesn't make 180. That's below 180. And if we take a look at these two angles, also formed by AD and BC, we'll see that 90 and 150, that doesn't add to 180. That's not supplementary. That gives us much more than 180 degrees. So since these same side interior angles are not supplementary, that shows that AD and BC are not parallel. And since this is a quadrilateral with only one pair of parallel sides, that means that it is a trapezoid. Finally, the last part of the question says to explain why ABCD is not a rectangle even though it has a right angle. Well, in order to be a rectangle first needs to be a parallelogram. And in order to be a parallelogram does need to have both pairs of sides parallel. Both pairs of opposite sides need to be parallel to make it a parallelogram. And as we see here, we only have one pair of parallel sides. AD and BC are not parallel to each other. So even though there's a right angle here, can't be a rectangle because it's not a parallelogram. Here we have a definition of what it means for a trapezoid to be an isosceles trapezoid. So a trapezoid is isosceles if and only if it has congruent legs. So if you take a look at this diagram of an isosceles trapezoid, notice that the two legs are marked as congruent. A trapezoid is isosceles if and only if it has congruent base angles. Now, since trapezoids have two bases, they have the upper base and the lower base, top base and bottom base, they have two sets of base angles. We have the upper base angles, which as you can see are congruent to each other in an isosceles trapezoid, and we have the lower base angles, which are congruent to each other in an isosceles trapezoid. So once again, if a trapezoid is isosceles, the upper base angles are congruent to each other and the lower base angles are congruent to each other. Here we have an example, and the first part of the question is asking us to find the measurement of angle DBC. So that's this angle over here. I don't know anything about this quadrilateral. Nothing else is given to us except some of the measurements marked in the diagram. And I see that angle DBC, this angle over here, is the last missing angle of triangle DBC. We have two other angles in the triangle, the 30 and the 70. 30 plus 70 is 100. So that means that angle DBC needs to be 80 degrees since all the angles in a triangle do always add to 180 degrees. The next part of the question tells us to prove that ABCD is an isosceles trapezoid. Well, before a trapezoid can be isosceles, it first needs to be a trapezoid to begin with. And they never told us that this quadrilateral was a trapezoid. So in order to prove that we have an isosceles trapezoid, we first do need to prove that we have a trapezoid to begin with. So remember, by definition, a trapezoid has only one pair of parallel sides. So if I take a look here, I notice that the 30-degree angles have the same measurement. And if I highlight the lines forming them and the transversal in between, notice that I have a letter Z. Both of these angles are in the corners of the Z. They're inside the lines, one's to the left of the transversal, one's to the right of the transversal. These are alternate interior angles. Inside the lines, different sides of the transversal. And remember, if alternate interior angles are congruent, that proves that the lines forming them are parallel to each other. So once again, congruent alternate interior angles prove that AB and DC are parallel to each other. Now let's take a look at the other two alternate interior angles that we have here. The 40-degree angle and the 80-degree angle are formed by these two lines and the transversal that intersects them. Notice how once again we have a letter Z, except this time it's a backwards letter Z. And in the corners of our Z, we have our alternate interior angles inside the lines on different sides of the transversal. Now notice that these alternate interior angles are not congruent. They actually have different measurements. So since the alternate interior angles are not congruent to each other, the lines forming them are not parallel. So AD and BC are not parallel to each other. Since quadrilateral ABCD only has one pair of parallel sides, that means it is a trapezoid. Now, we need to prove that this trapezoid is also isosceles. So remember, isosceles trapezoids have congruent legs. The thing is, they don't tell us that the legs here are congruent, so we can't assume that. We also know that isosceles trapezoids have congruent upper base angles and congruent lower base angles. We can find the angle measurements and see if the base angles are congruent. We already have almost all of the angle measurements here. We're just missing this one up here. And in triangle ADB, we have a 40-degree angle and a 30-degree angle. Together, that makes 70 degrees. So the last angle that's missing, I can do 180 minus 70, and I get 110 for the last angle. So let's see if the upper base angles are congruent. Let me get a different color. Here we go. This upper base angle is 110 degrees. And this upper base angle is 80 plus 30, which is 110 degrees as well. Now let's check if the lower base angles are also congruent. This lower base angle is 70 degrees. And guess what? This one is too. So we know for sure that we do have an isosceles trapezoid because we just showed that the base angles of this trapezoid are congruent, making it isosceles. Okay, now the last part of the question says to solve for x. Now that I know this is an isosceles trapezoid, I know for sure that its legs are congruent to each other. So I can make an equation that says that in order to find x. I can set up the equation. X plus 5 is equal to 3x minus 21. Subtracting x on both sides, adding 21 to both sides, I have 2x is equal to 27. Oops, sorry, I added that incorrectly. 26. There we go. Now, all I need to do to get x by itself is to divide 26 by 2, and I get that x is equal to 13. In this example here, it tells us in isosceles trapezoid ABCD, AB is parallel to DC, and the legs AD and BC are congruent. We also know, since this is for sure an isosceles trapezoid, that the base angles are congruent. So if this upper base angle is 2x, so is this one. If this lower base angle is 3x plus 5, so is this one. If measure of angle BAD is 2x and measure of BCD is 3x plus 5, find the measure of angle BAD. So we are looking for the measurement of this angle over here. Well, since I know that AB and DC are parallel, let me highlight my parallel lines cut by a transversal. Notice how 2x and 3x plus 5, these two angles here in the trapezoid, are same side interior angles, which we know are supplementary when we have parallel lines cut by a transversal. So I know that the upper base angle and the lower base angle below it have to add to 180 degrees. So let me set up an equation that says that 2x plus 3x plus 5 is equal to 180 degrees. Combining my like terms, I have 5x plus 5 is 180. Subtracting 5 from both sides, 5x is equal to 175. And all I have to do now is divide by 5, and I get that x is equal to 35. Now that I have my x value, I'm just going to plug back in to find the measure of angle BAD. So the measure of angle BAD is 2x, and since x is 35, 2 times 35 is 70 degrees. Here we have a theorem about isosceles trapezoids. If a trapezoid is isosceles, then its diagonals are congruent. So we're going to prove this together. So here I have a trapezoid, and I'll give it a name. I'll call it trapezoid A, B, C, D. And if we want to prove that the diagonals are congruent, then since this trapezoid is divided into triangles by the diagonals, I want to pick two triangles to focus on. And the two triangles I'm going to focus on are ones that have the diagonals as its sides, since we want to prove something about the diagonals. So I'm going to start with diagonal AC, and I'm just going to form a triangle that has AC as its side. Let me get my different color. Now let's go to diagonal BD, and I'm just going to make a triangle that has BD as its side. Now that I have my two triangles that I'm focusing on, I can see that they're overlapping. So a really good strategy for working with overlapping triangles is to take each triangle and draw them separately. That way, when we start marking our diagram, we can clearly see what belongs to each triangle. So let's think about what we're given here to work with. If a trapezoid is isosceles, so we're given that the trapezoid is isosceles. So already we know ABCD is an isosceles trapezoid, and we want to prove that if it's an isosceles trapezoid, it has congruent diagonals. So since we already know this trapezoid is isosceles, we already know some things about it. In an isosceles trapezoid, we know that the legs are congruent. So we know that AD and BC are congruent to each other. In an isosceles trapezoid, we also know the upper base angles and the lower base angles are congruent to each other. So I know that this lower base angle and this lower base angle are congruent. This lower base angle is angle ADC, and this one is angle BCD. And I know that whenever I have overlapping triangles, there's going to be something shared between them. And separating my triangles, I see that side DC is the same in both of the triangles. So I definitely know that DC is congruent to itself by the reflexive property. And we can see in the original diagram that DC is shared between the purple triangle and the blue triangle. Now that we know the triangles are congruent by side, angle, side, we can prove that AC and BD are congruent as well by CPCDC. Take a second and try to write the proof. Pause the video. I'm going to do the same thing. And you can see my So now that we've proven it, we know that it's always true. Anytime you see the word isosceles trapezoid, you also know that its diagonals are congruent. That's a property of isosceles trapezoids. Moving along, so we are going to skip a little bit so that this video doesn't go all day, and we are going to do a coordinate proof. I'm going to take a second and graph the trapezoid. So I called it the trapezoid, but we don't know it's a trapezoid yet. We want to prove that it's a trapezoid in part one. So by definition, a trapezoid has one pair of parallel sides. So in order to show that things are parallel, we usually use slope formula to show that the slopes are the same. So what I'm going to do is I'm going to find the slopes of the sides of this quadrilateral and see if any of them are the same. And it should end up that one pair of sides is parallel, which will make it a trapezoid. Okay, so TR and PA had the same slopes, so that means that they are parallel, and a quadrilateral that has one pair of parallel sides is a trapezoid. For part two, we want to show that the trapezoid is not isosceles, so we have a couple of options. Either we can show that the legs are not congruent, or we can show that the diagonals are not congruent. I'm just going to show that the legs are not congruent, so I would have to use the distance formula to do that. And when I did the distance formula for the two legs, I found that they have different lengths, so they are not congruent. And since the legs are not congruent, the trapezoid is not isosceles.